Hello, everyone. This is the homework video for Module 6, Electromagnetism, and it's talking about electromagnetic induction. So, for the multiple choices, question one, we have four circular loops of wire. They are placed in a uniform magnetic field directed out of the page. And which loop has the greatest number of magnetic flux, okay, that passes through it? So the answer will be D, to simply count amount of how many magnetic field line has passing through it, okay, and then the greatest area, okay? In a sense that flux is B times A, right? The larger the magnetic field, the larger the area, the greater the flux. Therefore, it is D. And so D has the larger area, and it also has more magnetic fields. Question two, a circular loop of wire with a cross-sectional area of 0.025 meters squared placed inside of a 0.001 Tesla uniform magnetic field as shown. The plane of the coil makes 40 degrees angle with the magnetic field. What is the magnitude of the magnetic flux experienced by the loop? Okay, so pretty straightforward application of the definition that the magnetic flux is B times A times cosine of the angle, but this angle is the angle between the magnetic field and the area vector, okay? So this 40 degrees is actually not this theta here. This 40 degrees is the angle between the plane and the magnetic field. What you want is you want to construct a normal vector or an area vector of this area formed by the loop, and then calculate this angle, which would be 50, okay? So you put in that number as your angle, you will get your final answer as D. Question three, we have a 50-turn coil, cross-sectional areas given, and tells you that the magnetic field passing through the coil is increasing constantly from 0 to 0.015 Tesla, and then over a period of 4 seconds. So you want to apply Faraday's law. Okay, so Faraday's law is equals to negative N times the rate of change of magnetic flux over time. All right, so let's calculate your changing magnetic field. So be aware that this is changing magnetic field instead of changing magnetic flux. So you want to move your area outside of the rate of change and then multiplies by your rate of change of magnetic field. Okay, so it should be quite straightforward. Continuing on, question four. A rectangular metal plate is moved into a uniform magnetic field as shown. Which statement is correct regarding to the direction of the induced current and the speed of the metal plate? Okay, so as it goes into it, right? So part of there's going to be a eddy current formed on the metal plate, and that by Lenz's law will oppose the changing flux. Therefore, that current in the field will push the plate outwards. Okay, so the speed is going to decrease over obviously. Therefore, it's either B or D. And then if you use your right-hand rule, only the current, right? If this is like the plate when it gets in, right? The current has to be um, sort of in this direction, right? For it to be repelled outward, right? Use your right-hand rule and motor effect. And then the other side should be like this. And this is a counterclockwise rotation. Therefore, it's D. It's pretty much just a combination of right-hand rule and Lenz's law. Question five. The north pole of the bar magnet is moved away from the solenoid at a constant speed v as shown. The pointer on the voltmeter connected to the solenoid is deflected to the right as shown. Okay. It produces a maximum reading of 4 units. If the same magnet is moved towards the solenoid with 2v without changing its orientation, what would be the correct reading? Okay, will be double as the speed because like the induction is proportional to the speed, right? So it's 8 units, and this time will be to the left because the direction of motion has changed. Okay, so that's why it's P. Question six, the diagram shows two coils wound around a solid iron rod. The coil on the right is connected to a galvanometer which detects current. Initially, the switch is open. When the switch is closed, what will be absorbed in the galvanometer? Okay, so that when the switch is closed, the coil on the left-hand side will immediately produce a current, and that current would immediately produce a magnetic field. And after that, it stays constant. But during the instant where it produces a magnetic field, there's a rapid changing flux, and that changing flux induces EMF on the right-hand coil, and hence currents, hence you will sense a detection. But as there's no more changing flux happening afterwards, so that EMF induced will cease to exist. Therefore, it will be selection D. A zero reading changes to a non-zero reading to indicate the rapid changing flux, and then goes back to zero. Okay. Question 7, it's you're given a plot for a graph for magnetic flux over time. You're asked to select the graph for EMF over time. So it's quite trivial. If you consider Faraday's law, the EMF is basically the gradient of magnetic flux differentiated with respect to time. Okay, so just the gradient function and then with a negative sign in front. So this is a sine curve. It has a gradient of cosine. You put a negative sign in front of it, so it becomes negative cosine. Therefore, I just choose a negative cosine function. Okay, so do this type of question in a more mathematical approach. It's very easy. Question 8, we have a loop inside of the outer page magnetic field. The graph shows the changing magnetic field strength over 3 time intervals, T1, T2, and T3. Which statement correctly describes the magnitude of EMF induced in the coil? So during the period from of T1, right, the flux is increasing, so we're going to induce a magnetic field. Sorry, we're going to induce an EMF. And T2, we don't changing the magnetic flux, so there's no induction. T3, we are decreasing the magnetic flux, so there's also induction in the opposite direction as in T1, but with a smaller magnitude in terms of the gradients less. Okay, so yeah, B is the right answer for this. Question 9, we have a coil that's rotating in a magnetic field. As the coil rotates, which statement is correct? So as it rotates, right, the area of the coil is the area vector of the coil is changing angle with the magnetic field. So due to this rotation, we have a changing flux and therefore EMF and therefore the currents, and therefore by Lenz's law, it opposes the initial change. So the rotation is going to be sort of restricted or minimized, right? And then you consider where is the changing flux being the maximum. It will be at this will be when the speed is faster, right? So the rate of changing magnetic flux will be greater, so there will be more sort of torque you need to do so because you want to have you're inducing a larger a positive current, so therefore you want to have a larger torque in order to rotate it. Therefore, it's C. Question 10, we have a magnet connected to a spring. A student is investigating electromagnetic induction using a bar magnet hanging from a spring that is fixed to the ceiling as shown. The bar magnet is pulled down so that it is inside the solenoid and then released. So it's going to go upward by the spring force. Okay, so the students noted that when the solenoid is connected to an ammeter, the bar magnet comes to a rest more quickly than it's connected to a voltmeter. Okay, so the reason that it goes back up quickly is because hold on, the bar magnet comes to rest more quickly than it connects to a voltmeter. So the reason that it comes to rest more quickly is because as the magnet oscillates, right, there will be an opposing force due to the induction of current. By Lenz's law, there's repulsive force, and ammeter is the one that allows current to flow. Okay, which indicates ammeter has a very small resistance, and hence it comes to rest earlier, as in this opposite force exists by Lenz's law. But then if you connect it to the voltmeter, it comes to rest slowly. This is because voltmeter typically has a large resistance. Therefore, that reduces the size of the induced current and then therefore the opposing force as well. Okay, so C is the right choice. It says that the voltmeter has a greater electrical resistance than the ammeter. Okay, it's pretty much just determine which the ammeter has a larger current, so it comes to rest earlier due to the induction, and then voltmeter is less. Okay. Question 11. We've got a 10-turn coil connected to a galvanometer. Describe how the equipment shown above can be used to demonstrate Faraday and Lenz's law. In your answer, include a relevant equation and expected observation in the galvanometer. So So I split this question in two dot points, okay, in the sense that I demonstrated Faraday and Lenz's law separately, okay. So beginning with the introduction, just by stating out what Faraday's law is, you always need to do this. Faraday's law states that when there's a changing magnetic flux, a temporal changing magnetic flux means a change that's like with respect to time, EMF is induced, and then you write down the mathematical equation. So in this case, we can stimulate a changing flux just by moving the magnet relative to the coil. Now, related to this case, so according to Faraday's law, we should have induced EMF and therefore current in the coil. So the occurrence of current, it will be indicated by the galvanometer, and then we can see like a needle that's being turned or something. So that verifies this our Faraday's law. And in terms of Lenz's law, again, start with the definition, and then the fact that you have to induce a current, which must be directed such that the initial change in flux is minimized. In this case, the galvanometer is able to detect the direction of the current by looking at the direction of the tip, right, of the needle. So therefore, the galvanometer is able to verify whether Lenz's law is true just by looking at the current direction, whether it counteracts initial change or not. Okay, so that this experiment is able to confirm both laws. Okay. In terms of question 12, we have a rectangular coil with dimension 0.1 and 0.07 placed into a pair of permanent magnets. The field strength is 0.5 Tesla. The coil is able to rotate clockwise about the axis as shown. Describe how the magnitude of the magnetic flux changes as the coil moves through half of a revolution from its position right now. In your answer, include a value of maximum and minimum flux passing through the coil. Okay. So I answered this question with a very extensive mathematical approach. You could also done it with qualitatively if you explain it very well, but I found it really hard to explain um, like a physical quantity that change with a mathematical model using just word. So I just choose to do the math way, which I definitely used a lot of like math symbols to try to model what's happening in sort of a function, and I plotted the graph as well. You will see. This is like, I think it's a better way to do physics. So the magnetic flux in this case, we define what it is, right? So that's everybody should do this, no matter you do the qualitative or quantitative approach. Okay, so the product between the B and then the area vector. Okay, so in that we have BA times cosine theta. Here, theta is the angle between the field and the area vector. As the configuration as shown now, the area vector is currently perpendicular to the magnetic field. Okay, so the A vector is orthogonal, which means perpendicular to the magnetic field. So we have a 90 degrees sort of phase shift. So the theta doesn't start from zero. At this point is where we start the motion, but here theta is in zero. Okay, so we have a phase shift. So 90 degrees phase shift. Okay, so we want some variable that starts from zero, so we can analyze this whole situation with like going from initial to final instead of going from like a 90 degrees to something. So we define some dummy variable alpha that represents the angle displaced during this motion. So angle alpha starts from 0 to 180, representing half of revolution. Okay, so phi in the term of this alpha as a dummy variable will be expressed as this with a 90 degrees phase shift. Okay, and then you can plot this function, which is a so remember anything, right? Cosine alpha minus like pi over 2 is equivalent as cosine of negative of pi over 2 minus alpha, because cosine is a even function, right? Remember that, and then that is also equal to sine of alpha. So I'll just elaborate that again. So cosine of negative x is equals to cosine of x due to its even function property. And then we just did that. So cosine of pi over 2 minus alpha, let's flip that, is equals to is equal to sine of alpha, right? This is a trig property you should know. So we just plot a simple trig function, but we only worry about alpha being from 0 to pi, so that's just half of a revolution of a sine function, right? So this is the graph I plotted. You should be able to plot this graph, like if you're doing at least 2-unit math, right? By now, you should be able to do this in year 11, and you should be able to do this now. So I don't see this is out of the syllabus for physics. I see this as a smart choice for explaining this question in a more convenient way. Okay, so you see the graph that indicates the motion, right? So the flux goes from 0, increase to a maximum. You can even calculate what is this maximum, which would be the amplitude here, simply b times a, right? Which you can calculate it. And then it goes from maximum back to 0 from when it's 90 degrees to pi. Right? It's very simple explanation, and then you graph everything out. Okay. So if there's any questions on this, come and see me, and maybe explain it qualitatively. Question 13. A 30-turn coil with a cross-sectional area of 0.044 meters squared is placed in a magnetic field produced by a pair of electromagnets. The magnetic field is perpendicular to the cross-sectional area of the coil. Here we have a bunch of data, right? And anytime you see this data, it's time for you to derive a theoretical equation. So we have a relationship between time and magnetic field. It's changing and the time is changing. So we're going to have a plot, okay? So if you look at question B, it says to use the graph calculator changing the magnitude of EMF produced. So this is our model. Yeah, we'll get you the theory later, but the plot just goes like this, right? Again, I have designed the grid so that you can plot everything nicely, okay? Yeah, so question B says to use the graph. So again, we have to consider the theory. The Faraday's law states epsilon is equal to negative n d phi dt. And area is not changing, so we factorize out A away from phi, and then we leave B as the differentiating term. Okay, if you are good at math, you should know dB dt is exactly the gradient in this graph. Okay, and right, so just calculate the gradient from the line of best fit, use divides over run, multiplies by area and n to get your voltage. I forget to add a negative sign here, but I don't think that matters a lot. Okay, so it's pretty standard. Let's move on. Question 4, this one is a good one. I end up writing so much for this question that I think it shouldn't just be 5 marks. But even if this comes out in exam, I still encourage you to write as much as possible, as detailed as possible. So what I did for this question is I pretty much go into the full detail of this question. Okay, so that's all I can think of. If I can write more, I could just I would do some like math that's outside the syllabus, try to calculate, the some of the mathematics sophistications, which I won't get into here. This is outside of the high school syllabus. Question 14 says that a solenoid is attached to a spring balance, so you can measure the amount of force from it. It is positioned directly above the solenoid, and initially the switch at the bottom is open. Explain how the mass reading in the spring balance will change when the switch is closed. Your answer should include information about the current direction of the top solenoid. You can annotate on the graphs to indicate the current direction. Okay, so this is what I did. So the closing of the switch will initiate a current. Okay, at the bottom coil, this current produces a magnetic field such that the current, creating a south pole on the top and north pole at the bottom for the bottom coil. The steady flow of current and then sustain this magnetic field. Because this rapid changing field, right, the top coil actually experiences a rapid changing flux when immediately after the switch is closed. And then the changing flux will reduce to 0 because no more flux is changing due to the steady flow of current. By Faraday's law, an EMF will be induced due to the changing flux. And in this case, EMF as well as the current will be induced on the top coil. And by Lenz's law, the current must be directed to counteract into changing flux. Therefore, this is what I draw. So in order to counteract the initial changing flux, we are producing the south pole here. The flux must minimize, all right? The induced current must minimize this south pole's flux. So it's going to produce another south pole facing the south pole. right, such that they repel each other to reduce the flux, okay? And if you use the right-hand rule, the current should be directed like this, okay? Yeah, so a current flowing from X and Y is induced so that um, the at the moment of the closed switch, the top coil experiences an upward force and therefore repel from the bottom coil. This is me counteracting the changing flux. So this force quickly diminishes after the flux stops changing, right? And therefore we have no more change anymore. Well, we haven't really explained about the readings of the spring, which is what the question is asking. So let's talk about that. In order to talk about that, we need to consider what's going to happen to the coil mechanically. All right. So analyzing the motion in terms of before we apply this opposing force and after we apply this opposing force. So prior to the opposing force, the top coil is balanced. So now every force is balanced. We have the spring force balances with mg. So the spring is holding the coil, not falling back to the ground, right? So we have this equation. And then just a little bit of the background. The spring force and is proportional to sort of the compression or elongation of the spring. So if you stretch a spring, you will get a stretch a spring longer, you will get a larger sort of tension force. If you compress the spring uh, a lot, you will get a pushing force. Okay, so this equation demonstrates that where x is the displacement from the spring's natural length. Okay, the equilibrium position. During the action of, and I also define like an axis so that this is like the spring's natural length, natural sort of position. You can compress it, you can elongate it, and you will produce different force accordingly. Okay. During the action of the opposing force, the net force momentarily breaks away from zero because now you have an extra magnetic force, which causes an acceleration from Newton's second law. Okay, that acceleration will move the top coil upward. Okay, so after the action of this opposing force, the coil will be pushed upward by some displacement. We don't know exactly how much is it. It depends on the strength of the magnetic field. We don't know about that. So we then because the changing flux stopped, so this force no longer exists. So it just turned on for a while, and then suddenly it just turns off, right? So the coil moves up, and then suddenly there's no more force like this to push it up. So it's gonna be pushed down by the spring force, right? So yeah, so the Fs force the spring force due to the upward displacement will now be larger, okay? Sorry, will now be lesser, so that the mg now takes more advantage than your spring force. Because originally, right, the weight force elongates the spring, and then your magnetic force sort of liberates a little bit of elongation. Now, after the magnetic force applied, the displacement causes the spring force to decrease. Therefore, your mg is currently larger. So now the coil will accelerate downwards. Okay, so it's gonna be pushed upward and then move downward as well. It's gonna oscillate. Okay. But after it has moved downward, you're sort of elongating the spring again. So to a point where the Fs is now like sort of larger than mg, so you sort of go back up again. Okay, so now you get this continuously up and down oscillation. Okay, it's just what a spring does, right? So up and down oscillation. Okay, so you want to mention that as well. So it oscillates about an equilibrium position where Fs is equal to mg. Yeah, so I would say this is very sophisticated, and the fact that you need to, if a student mention anything about oscillation, I think that's good enough. Okay, I just went into more detail about why zero oscillation, and then specifically about the forces that's acting on it. Okay, and then about like the equilibrium position of the oscillation as well. Okay, so. This is it for this question. I'll pause here for a while just for you to maybe take a screenshot if you want to copy the answer. I didn't use dot point for this question because I sort of did for the second half, but yeah. Right, for question 15, a metal rod is sitting on a pair of parallel metal rails and then connected to a wire as shown. Question A, the experiment is repeated with an external magnetic field applied upward, perpendicular. Okay, so it's two experiments. The first one is the rod just fall down due to gravity. The second one is the rod fall down due to gravity, while at the same time there's a magnetic field. So the rod is a conductor, and then the wire on the top makes sure that this forms a closed loop, so you're going to have a current being produced. Explain why and how the motion of the rod will be different. So exactly two dot points mentioning about the one without magnetic field and then the one with magnetic field. So when there is no magnetic field, the conductor simply slide downward due to gravity, during which gravitational potential is fully converted into mechanical energy. This involves rotational energy, translational energy, and friction, and all other mechanical energies. When there is a magnetic field, things becomes more complicated. There is relative motion between the rail and the magnetic field, which causes changing flux. You could also mention, what is it? You could also talk about the motional EMF in this case, right? And then define Faraday's law, and then say about current, and then use right-hand rule for Lenz's law to determine the direction of current. Right? It turns out to be clockwise like this. So this current end up opposing the falling motion of the rod. So, as in this case, the opposing force reduces the downward net force on top of gravity. Okay, so you have to say it only reduces the downward acceleration. It cannot oppose initial downward acceleration. Otherwise, the rod is not going to go up. It's always going to go down, but with a smaller downward acceleration. Okay. It's not going to overcome the downward force, only going to minimize. So the acceleration is the one that's being reduced. Okay. So resulting in a slower motion, and this is also consistent with energy conservation, as now that the gravitational potential energy not only goes into the kinetic energy of the rod, but also converted into some proportion into its electrical energy. So it gains less kinetic energy, end up moving slower. Okay. So yeah, just basically talk about the mechanical details involving acceleration, velocities, and also talk about energies. Very helpful. Question 15, identify one type of energy transfer. So we have gravitational potential goes into kinetic. You could also mention potential goes into electric, but you cannot say kinetic goes to electric, okay? Because kinetic energy is not being reduced. Kinetic energy actually increases all the time, okay? It's the potential that goes into the electrical potential, okay? All right, so question 16, this is the beast, okay? I wrote a lot for this question. I think at the end of the day, it should be 9 mark instead of 7 mark. But yeah, so a student performs experiments. We sort of done a very similar question in examples during lesson. Okay, this one has some quantification aspects into it. So it's a 2 kilogram magnet dropped from rest to above a plastic, aluminum, and copper tube. Okay, and then the height is given, so you can calculate the potential energy and all that. The table values are given for the speed of the magnet when they exit the coil, sorry, the tubes, which you can calculate the kinetic energies of. Okay, so we can analyze this experiment. I know that this experiment uses Faraday's law length extensively, so I put it into an introduction where I define all the laws at the same time. Okay, and then I split it into dot points talking about each tube specifically. Okay. So these scenarios involves electromagnetic induction as the magnet falls through the tubes. Changing flux is a result from the relative motion. Then by Faraday's law, where an EMF will be produced in each case, right, as epsilon is equal to phi dt, uh, in shape of loops and on the surface of the tubes. So that's defining Faraday's law. So the cases involving copper and aluminium as conductors, right, and induced current will then occur as a form of eddies, so eddy currents. Okay, so the currents, according to Lenz's law, will seek to minimize nature changing flux, thereby pushing the magnets with an upward force. Okay, and then the discussion of each tube in more detail is as follows. Okay, and then I use dot points. I mentioned talk about plastic tube first. So plastic is a non-conductive medium. So as well as the EMF is still being induced, current will not be formed because it has a large resistance and cannot form a current. Therefore, no opposing force effect. Okay, so hence the magnet resembles a free fall motion, and by energy conservation, gravitational potential is converted into kinetic of the magnet, and also a bit into the aerodynamic drag. Because if you calculate it for the potential energy, mg delta h, that's literally delta h here. Okay, m is given, g is gravity. Right, so you can calculate the potential energy. This is the total energy in the system. So all of the other energy that's been converted has to came from this energy. Okay, so delta U, as we fall, we have a changing delta U by decreasing amount by 27.44. And then we should use the value for plastic tube. We can calculate for the kinetic energy, right? Ideally, all of the potential should just convert to kinetic energy without anything lost, okay? But then if we calculate it for the kinetic, we get 27.04, which is not exactly that, right? It's close to delta U because, yeah, like it's directly going to the kinetic energy, nothing else is given, okay? But this difference suggests an energy loss due to air friction. So you just sort of have to be very inventive, right? Because this question didn't give you a hint that there's air resistance, but you need to be able to think of that on the spot to be able to get full mark for this question, okay? Just by noting the difference in the energies. You need to have that sense of common sense here, okay? So then you can calculate the energy loss due to air friction simply by calculating the difference between the energies, okay? That's what I did. 0.4 joules of energy lost due to air resistance. We're going to assume the same amount of air resistance happening for other tubes as well, because why not? They're also moving in the air, so there's going to be this energy loss as well. And then we move on to copper tubes. Copper tubes will have inductive eddy current present, and therefore the opposing force, so making it fall slower, right, with a slower acceleration, okay, with a smaller exciting speed of 2.3. Well, in this case, copper is a better conductor with a smaller resistivity so that the induced current will be larger in magnitude. Okay, therefore the energy consideration here, we have more induction happening. We dissipate more energy into electrical. So gravitational potential energy not only converts to kinetic and our aerodynamic drag, a larger portion of this goes into the electrical as well, and then later dissipates into heat because eddy currents always ends up into heat. Changing potential is still that. And delta K, if you use the value given in the table, you can get 5.29 joules. So this is like, it's a big difference compared to the one we get before. In plastic tube, it's 27.04. It's almost exactly equal to delta U. But in this case, it's only 5.29. So actually, if you work out the amount of energy, if I define delta H as in the energy lost into the electrical energy, uh, considering the energy lost due to friction, you can calculate for delta H as well. It's equals to negative 21.75. This is a huge drop, right? There's a big portion amount of energy lost into electrical. And this is why in copper tube, it falls much slower than plastic tube. Okay, so just sort of explain that. Aluminium tube, on the other hand, is still very similar to what copper tube does, with the only difference that aluminium has a larger resistance, so the current induced will be less, so that the opposing force will be less. Okay, so less energy will be dissipated into induction here and onwards, but it still exists. Okay, so still slower than a plastic tube, but gonna be faster than copper. Okay, if you do the same energy analysis, you get that the energy lost into electrical is much smaller. It's only 7.68. And then sort of write a conclusion, right? So which one falls faster, right, as this question concludes. Okay, it is quite a challenging question. To get full marks, you need to be able to notify how there's a air friction happening, and you be able to calculate all the energies and explain it in a cohesive way. So yeah. I mean, I wrote 2 pages about this, 2.5 pages. So if you didn't really answer up to this level, it's very expected. Yeah, but at least if you mention everything that I sort of mentioned, but not in exact detail, it should be fine. Okay. Question 17. Question 17 shows you a graph that when the magnet is falling through a tube, and then this graph shows the changing EMF that's being induced. So the graph looks like this. It starts at 0 roughly, and then increases to a maximum and decreases to a larger magnitude of EMF, and then back to 0 again. Okay, so this would corresponding to the location where this maximum is where the changing flux is maximum. So that's when the North Pole is sort of like inside this magnet like this, when it just enters the magnet. But when the magnet is sort of in the middle, right? When the magnet is in the middle, now the changing flux on the top half of this coil is in a certain direction, while the bottom half of this coil is in the opposite direction. So that in total, the EMF will be balanced out. Okay, because the top half is trying to attract the south pole upward. So it's going to induce north pole here, right? And then the bottom half, when the magnet is here, it's going to induce a north pole trying to repel this, right? So this current will be opposing, induce will be opposing each other. Therefore, the EMF actually reduces to 0, okay? And then as the magnet falls downward, when it exits, right, it goes up to the maximum again because it's trying to attract it back in, right? But now the direction is opposite, okay? Because now I have to use a south pole to attract this, sorry, I have to use the north pole here to attract the south that's falling off. But when it goes in, I have to use the north pole here. So you are flipping the polarity in this case. So the direction of EMF has to be flipped. It has a larger magnitude of EMF induced is because the magnet, although experiencing this opposing force, but it is always accelerating. Remember that the opposing force due to electromagnetic induction is only minimizing the initial change. So it's not opposing or overcoming the initial change. It's still going to accelerate downward. So as the magnet still gains speed, as it exits the magnet, it's falling faster than when it enters. So the changing flux is greater. Therefore, this is why we have a larger magnitude of EMF induced there. Okay, so yeah, this is part A. That's why how I explained it. Yeah, and then part B is to graph if the magnet is dropped with a greater height and then south pole pointing down. So if it's dropped with a greater height, it enters the tube at a longer sort of. You have to delay the time a little bit, right? So it enters the tube, needs a longer time to enter the tube. So your peaks need to be delayed. Okay, that's one thing you need to mention. The other thing to mention is that the graph needs to be flipped because now we have flipped the polarity of the magnet. So now the induced current will be completely in a different direction. Okay, so it goes downward first and then upward. Okay, and then the other property sort of follows, right? Just go downward and it goes upward with a higher magnitude. So one more detail you also say is that the sort of the width of this profile is going to be thicker than the width of this profile. It's because that the magnet exits the coils faster when it goes out of the coil because it's faster. Okay, so something like this should be fine. Right. So, and then we have the challenging question. It's pretty much an application of Faraday's law with you actually need to differentiate something instead of using an average change. So it's given that the magnetic field at different location away from the coil as this function, they can calculate it, right? Typically with a dipole, also used with an electrical dipole, it's always proportional to the distance to the power of the cube, to the power of 3, inversely proportional to that. So it's very common thing that you will observe. In 2023, I think, the 4-unit math exam involves a question that they modeled the strength of a magnetic field like this. Now, they don't really talk about the physics in math, but they use this model, so it's exactly the same thing. Yeah, so and then the EMF, you are supposed to derive for the EMF using Faraday's law, and then you get this form. Okay, so the idea is to use definition of Faraday's law, rate of changing flux, and area as constant to differentiate B with respect to time. But B is a function of x, and x is a function of time, so you need to apply chain rule. Okay, so dx dt times b dx. Dx dt is negative v as we are moving towards the coil, and then by the definition of x-axis, it's sort of decreasing x, so it's negative v. And dB dx is you need to differentiate this whole thing. Okay, so it's just -3 times k divided by x to the power 4. And then a, if you substitute for pi r squared for the circular coil, you'll get final answer is this. Okay, so it's really not that hard. It's easier than question 17 and 16. Okay, just a bit of math. All right, so that concludes it for this week's physics homework. I'll see you next time.